All right, so let's see how much we can get through today. We are slightly ahead of schedule, but you know, it is best we are ahead. We will not try to waste time, but we'll just push on with the module. So let's start by reviewing briefly what we have done so far with two-port networks in terms of the parameters. So we spoke about your standard two-port network in terms of the input and output currents with respect to the voltages. And we indicated that these were described by your admittance parameters, your Y parameters. We also, which is shown, of course, with the equations that are on screen. Yeah, and then we also looked at the input and output voltages, your V1 and V2. V1 and V2, which were given by the currents, I1 and I2. And of course, we looked at how you would determine the individual parameters in terms of whether we open circuit or short circuit a port. Short circuiting done to make our voltage zero, and open circuit, having it in an open circuit, having it open circuited, to make our currents zero. So those are the admittance and impedance parameters. Today, we want to take it one step further. Or before I go further, any questions regarding the admittance and impedance parameters? Is there anything that you're unsure of? Anything that I said that is, still fraught with all the mud? Any questions? No? All right. So we want to move on today and look at our hybrid parameters. And simply put, hybrid simply means mixture. So we have a hybrid vehicle. It means that you use both electricity and gasoline as the sources of energy. Right? So hybrid just means mixture. So in terms of the hybrid parameters as applied to two-port networks, they are used to determine the input voltage and the output current with respect to the input current and output voltage. So whereas the impedance parameters, we're looking at the voltage with respect to currents, and the admittance, we're looking at currents with respect to voltages. For your hybrid, we're looking at both voltage and current with respect to current and voltage. In other words, mix up, all right? So the equations for your hybrid parameters are shown. So for the input voltage, yes, we have V1, and that is based on the input current and the output voltage. And for the output current, which is I2, with respect to the input current and the output voltage. So that's the reason we call them hybrid, because it's a combination of parameters that we're looking at. Any questions? Okay, so are we finished with this?
No, sir, just a second.
All right, so we can move on now. So in matrix form, we have V1 and I2 being equal to H11, H12, 21, 22, I1, V2. Of course, in terms of the subscripts, the 1, 1, 1, 2, and 2, 1, and 2, 2, same representation in terms of, yes, they tell us the position in the matrix, but it's telling us which port is being divided by which. So for H11, it would be a port, it would be port 1 or parameter in port 1 divided by another one in port 1. 1, 2, 1, port 1 and port 2, 2, 1, port 2 by port 1, 2, 2 will be port 2 by port 2. All right? So if we apply superposition to these equations, and again, we know how to make each of these variables 0. So let's start with H11. For me to get H11, yes, for me to get H11, it means that I'm going to make V2 0. So for H11, right, with V2 0, it will be V1 over I1. Yes? So, Mr. Swaby, H11 is equal to V1 over I1 based on what we have learned so far. Yes, what can you say about H11? What would it represent?
It would represent the hybrid parameter when V2 is...
Yeah, man, but we're dividing up voltage by a current. What does that give us?
Voltage by current, that would give us impedance. Yeah.
All right, so it's an impedance. Good. Yes. Next, we're making V2 0. So what name would we give to this?
It would be a short circuit. Since it's not between two ports, it wouldn't be transfer, so it would be a short circuit hybrid, sir, without the transfer.
All right, you just told me it's an impedance, so keep that in there. So it's a short circuit impedance, but where is this impedance?
At port 1, sir.
Huh?
At port 1, sir, looking into port 1.
Yeah, so what we call that?
The input impedance.
All right, so give me the name now.
So the name would be the closed circuit input impedance.
Make it closed circuit. When that come in? You didn't tell me anything about closed circuit.
Short circuit.
Short circuit, sir.
Short circuit. Okay.
Short circuit input impedance.
Thank you very much, Mr. Sweden. I know you could handle it. That's why I continue to press. All right. So H11 would be an impedance because we have voltage divided by current. V2 is made 0, so therefore it's a short circuit parameter. And so H11 would be a short circuit input impedance. So if we now look at H12, any volunteer?
Yes, sir.
Yes.
Okay, go ahead, Mr. Facet.
Open circuit transfer impedance. I mean, yeah.
Huh?
Sir.
Sir.
All right, sir. I heard. All right, go ahead, Mr. March. Go ahead.
All right, so seeing that we have voltage upon voltage, sir, we would get a constant, sir. And the constant can be referred to as, we call it a gain. However,
What?
This gain, however, gain is equal to the output upon input. Therefore, this will be reversed. This will refer to as, I think, the it will be a reverse gain. However, seeing that it's you're getting a zero current circuit, that means you're open circuited. So I think it's an open circuit reverse gain.
All right, I can work with that, but it's all like you didn't know before. Right?
So a read, sir.
So you're confirming it, right? So you're correct. A voltage gain would be output over input, right? Therefore, if we have input over output, it would be a reverse gain, yeah? It would be the reverse of the gain. So H12 is the open circuit reverse voltage gain. All right. So let's see now. Mr. Atkinson?
Yes, sir.
Looking back at the set of equations that we have for the hybrid, how do we make, what is H21? Let's look back at the equations. So we're now looking at equation, well,
I guess H21 would have been V2 over V1 with I2 open.
come on, look at the equation, look back at the equation. This is our set of equations.
Mm.
You see H22, H21?
Yeah.
Huh?
Yeah, I'm gonna say H21.
Okay, so if I want H21 for equation 2, what would I make 0?
You'd have make V2 0.
Okay, so if V2 is 0, what is H21?
Oh, well, H21 now would have been V2 0. That means your short circuit V2. Short circuit V2, and
Okay.
it would then be short circuit V2, then it would be V2 over V1.
No, but V2 is 0. That's 0. So what are you left with in equation 2?
H2, I1, and I2.
Okay, so what is H21? From what is left?
Okay.
Did we realize it's so easy?
I2 over I1.
All right,
I2
so,
over I1.
okay, so it's I2 over I1. Now, based on what we just said about H12, you now tell me what the name that would be applied to H21.
So
Based on what you just said.
So that would be I2 over I1, which would have be the output current over the input current.
Mm-hmm.
Yeah. And the short circuit voltage. Now, so you want a name?
Yeah, man. Based on what we just said, we said that H12, right? And we gave the explanation. We have given the explanation why we call it reverse voltage gain. Now you have H21. Yes.
Okay, so maybe this is just the current gain. Is there such a thing? It would be a current gain. It would be
Okay. Give me further define it for me.
So it would be the short circuit current gain.
All right. Excellent attempt. However, just for consistency, instead of just saying current gain, because we use the term reverse for the voltage gain,
For the forward.
we say forward for the next one. All right. So H21 is I2 over I1 with V2 being equal to 0. And so that is the short circuit forward current gain. Who wanna take on H22?
Me, sir.
All right, go ahead, Address.
H22, in order to get H22, you'd have to make I1 equal 0, which is open circuit. So given that the H22 formula would be I2 over V2, I over V is the inverse of impedance, it's the admittance, right? So, and both are on the output end. So it would be an open circuit output admittance.
Precisely. I like the reasoning. And to further highlight the fact that we have a mixture of parameters, which is why we say they are hybrid parameters. So these 8 parameters are hybrid, meaning mixture, yes? To highlight that, we have impedance, we have admittance, we have current gain, and we have voltage gain. You don't want it more mixed up than that. So that's why we call these the hybrid parameters. So we have the formulae for the various parameters for H11, 21, 12, and 22. Good. So we're going to go back to that little network, those 3 resistors that we had before, and we're going to derive the hybrid parameters from scratch. Now, you have to use, students, you have to use the definitions that we give. Meaning, for H11, yes, H11 was based on V2 being equal to 0. So it means that we would have short-circuited the output terminal or output port, yes? Similarly, H21, again, would be with V2 being equal to 0. Yeah? I mentioned this because Z11, when we found that it was with the output port being open circuited. You with me? So sometimes persons will and of course we're dealing with an impedance. So Z11 would be the open circuit impedance. But H11 is the short circuit input impedance. You understand? All right, so let's go back to our little network. That's our network. And we want to find H11, which is V1 over I1 with V2 being equal to 0. So let us short circuit the port. So I've just short circuited the port. Yep. And now we are going to find H11 with the short circuited port. So if I'm looking into port 1, what would be the impedance?
Uh, 5 is in parallel with 10.
5 in parallel with 10. To give us 50 over 15 or 10 over 3 ohms. Now, if I maintain the short circuit, I can now go and find H21. Yes, and H21 is I2 over I1. All right, H21 is I2 over I1 with V2 being equal to 0. So question, based on what we have before us, what would be the relationship between I1 and I2? First of all, where is I2 flowing? Yes, Mr. Black?
So you hear me?
I'm hearing you now.
Yeah, I2 is going into the 10 ohm resistor.
All right, so it's going through the 10 ohm and it's also flowing through the short circuited path, right?
Yes, sir.
All right, so no current going through the 20. So if the current I2 is going through the 10 ohm, Mr. Black, what would be the relationship between I1 and I2? How would I find that? Mr. Black?
Sir?
Yeah, man, how would
Sir,
I
do
find what's the relationship between I1 and I2?
could it be said that I2 is equal to negative I1?
But I1 wouldn't be the current through the 10 ohm.
Oh.
Yeah, Mr. Stewart, that's your hand. So Stewart, you didn't raise your hand for a purpose?
Sir, would it,
Hold on, Mr. Atkinson. Anyway, go ahead, Atkinson.
sir, would it be the negative of use the current divider rule and find the negative of it to get I2? So it would be.
Thank you very much. Because there'll be a component of I1 going through the 10 ohm, which of course would be I2. So we can apply current divider. Yes. So minus I2 would be I1 divided between the 5 and the 10.
Ooh. Oh, sorry. Apparently my mic wasn't working, sir. Sorry.
All right. So from this expression, we have minus I2 is equal to 5I1 over 15. We cross multiply, we get I2 over I1 to be minus 1 over 3. So H21 is equal to minus 1 over 3. And I trust you realize that all we are doing is applying the little things that you learned in Networks 1, right? So you know I'm not going to wait on you, because you're supposed to know all of this already. All right. So next we find H12. All right? So we can find H12. Now, in finding H12, which port are we looking at? Which
Port 1, sir.
Port 1. Now what we have at port 1? How is port 1 connected?
Sorry, we open circuit port 1.
Open circuit. So it means we're not doing a thing to port 1. So with port 1 open circuited, yes? Ms. Hanson, what's the equation for H12?
Oh, you just find the relationship between V1 and V2.
So what's the equation for H12?
Oh, the V2, 5V2. H12, sir. Yes, sir.
Is equal to?
Yes, so I do the H12 is equal to V1
Brianna?
Divided by V2.
Okay. And what's the relationship,
Yes, sir.
based on
Sorry
what
about
you're seeing? What's the relationship between V1 and V2? What expression would you use?
Can you divide up the voltage, sir?
Go again?
We would use voltage divider.
Between what?
Between for the V2, sir, you just basically divide up the voltage between the 5 and the 10. Hello?
All right. So we're looking at V2. All of V2 would be across the 20 ohm resistor. All right, so we're looking at V2. V2 is across the 20 ohm, but we want to find V1. So it would be voltage division between 5 and 10. Everybody comfortable with that?
Yes, sir.
And so H12 would be a third.
Sir, could you say that again, please?
This is what we're finding. The port that we have made adjustments to, and I put that in quotes, yeah, is port 1. So we're looking into port 2 and finding the relationship between V2 and V1. All of V1 is across the 20 ohm, so it means that V2 is being divided between 10 and 5. We want the voltage across the 5 ohm, so it's 5 V2 over the sum, 10 plus 5. So we get a third.
I'm assuming circle. Go back one more, please.
All right, so let's volunteer for H22.
All right, thank you.
So tell me what you want, what you would need for H22. Let's keep the circuit. We want H22. So H22 is equal to? Hello, folks. We only have to be
I2 over V2, sir. I2 over V2.
All right, let's try that again. So say I2 over V2. Professor Dixon, we can't deal with that. If you're going to have that background, I don't want to hear much from you for the rest of the class. That's too noisy for us. Ms. Richards? Folks, I tell you, don't come to my class, put up your photo and leave. I will remove you. So, Brian, I2 over V2, what's the condition?
Yes, sir. I2 over V2.
What's the condition?
Well, the condition is that
You have to think about it, you're not sure. It's I1 equals 0. So how would you go about finding the relationship between I2 and V2? Huh?
I'm not 100% sure, sir.
Well, tell me the 20% that you are sure of.
I'm sure. So I'm not confident to the yet, sir.
So I'm asking you, what's the relationship between a voltage and a current flowing into a circuit? If we're having challenges with this, maybe we need to just pack up the module from now.
Sir, the ratio, the resistance that's in the circuit with them.
So what's the relationship between I2 and V2?
The increase 20. So I'm nervous, sir.
Why you nervous, sir? Who in the class, you know? You know anybody else? Why are you nervous? Come on, Mr. Brand. Just tell me what you know.
All right, sir. Well, 20 V2.
So, Brian, I'm asking you. Okay, let me switch it around. If I asked you what's the relationship between V1 and I1, what would you tell me? What would you say to me?
Sir, it's not coming to my head.
You're scaring me now, sir.
No, sir.
Mr. Beckford.
Sir.
Mr. Beckford, help us out. Yeah, it's obvious you either weren't at your computer or you weren't paying attention. Mr. Beckford. But we will correct this in short order. Beckford, where are you? Oh, so this is the plan. You guys come put up your name and disappear. All right, let's start. You know, let me take the register now. Answer to your names. Blackwood.
Yes, sir.
Sawyers.
Yes, sir.
Well, Dixon, you showed to the one away already. Stevenson, Mr. Dixon, I'm not sure how you can learn with that noise in the background. You know. Stevenson. All right. Richards.
Yes, sir.
Oh, Delia Richards.
I'm here, but I just came to my computer.
Yeah, we know. Beckford. Beckford. All right. Morrison. David.
Yes, sir.
All right. Parker.
Yes, sir.
Thompson. Brown. Imani.
Here, sir.
Haynes. Javon.
Here, sir.
Cameron.
Yes, sir.
Are there? Okay. Richards, Joel.
Yes, sir.
Cahoon.
Yes, sir.
Hodges. Well, yes. Morgan. Morgan.
Yes, sir.
What being?
Yes, sir.
Where are we? Buchanan,
Yes, sir.
Peru,
Yes, sir.
Campbell,
Hello, sir.
Richards, Romain. Yeah, you answered already. Tariq, Gail,
Yes, sir.
Williams, Travis,
Yes, sir.
McFarlane, Vaughn,
Present, sir. Present.
Bora,
Yes, sir.
and Powell.
Yes, sir.
All right. Okay.
Sir, I never hear my name.
Yes, sir. I didn't hear
Who is that?
my name.
Richards?
No, Hanson.
Let me Hanson when I talk already, man. I don't know say that.
Oh, all right, sir.
All right. So, folks, we all have to be present. Eh? We can't be distracted during this thing. This is not something, if you could learn it just by video, then I would just send you to the videos. I already have postings on this thing already. You all need to be engaged. All right? This is just the tip of the iceberg. And if you don't get this, then it's one whole topic that you will lose. You'll lose out on. So I go back to you, Mr. Brian. Sorry if you thought I was going to leave you. So I'm asking you the question again. If I asked you for the relationship between V1 and I1, as a matter of fact, we already did it. What did we do in finding the relationship between V1 and I1? Chad Brian.
Yes, sir. What did we do?
Yeah, man, you should have it in your notes.
Yeah. We open circuited port 1.
Well, forget about the open circuit. What did we do? How did we find a relationship between I1 and V1?
Oh, I1 and V1. Okay, hold on. We short circuited port 2.
Somebody help me. Ms. Richards, what did we do? How did we find a relationship? Mr. Brian, is that right? How did we find a relationship between V1 and I1? Ms. Richards? You gone away from the computer again?
Circuited.
Pardon me?
Hello?
Go ahead.
Sir, I'm here. The internet is not good, but I'm trying. I said short circuited. Is that the answer?
Yes, we know about the short circuit. I'm saying, how did we find the relationship between V1 and I1? What did we do?
Maybe V2.
So you assess the direction, you assess where.
Mr. Brian, you had your chance. Yes, Ms. Richards.
So I said short circuited. Short
Mr.
circuited
Gill.
that make V2.
All right. Mr. Gill. Mr. Gill, I saw you raise your hand. Help me.
Yeah, V1 over I1.
Sir, the relationship, sir, is V1 V is equal to I times the impedance.
So we simply use V equal I times Z.
Yes,
that's the relationship. So we found the impedance, right?
Yes, sir.
Now, Mr. Brian, I come back to you. That's all I'm asking. What is the relationship between V2 and I2?
The admittance. Since the first one was impedance, because V1 over I1, wouldn't it be admittance if it's I2 over V2?
All right. Ms. Campbell, what's the relationship between V2 and I2? That's why you raise your hand.
It was an accident, sir, but I would say it is it would be 20 in parallel with 10. Sir, you have to. Sir, you want to find V2 over I2?
Yeah, but I just want to know, how are they connected? How are they connected? What's the relationship?
Sir, well, the amount of I2 that is flowing into the 20 ohm branch, you could have used that to determine it.
You started out all right, but you're gonna off track now.
Sir, because you kind of make me nervous, you never say anything.
I am hundreds of miles away from you. Mr. Atkinson, no, not Atkinson. Stuart, you're raising your hand again. Let me hear what you said. I can't believe you guys have me here for over 10 minutes. So.
I was just about to say that it would be equal to the reciprocal of 20 in parallel with 15, because you'll be finding the admittance of the circuit.
Hold on. Maybe it is my questioning technique that is poor. The relationship between V2 and I2 is that V2 equal I2 times the impedance. That's how I go. That's the relationship. Agreed? It therefore implies, as Mr. Stewart was trying to say, that I2 over V2 is going to be 1 over Z2. So all we are looking for is the impedance looking into that port, and then we find the reciprocal, which is what Stewart was saying. That is all I have been asking for the last 10 minutes. So, Ms. Campbell was now saying it is 20 in parallel with what? Come back to me now, Ms. Campbell. 20 in parallel with what?
Sir, 20 in parallel with 10 ohms.
All right, so you tell me now, Ms. Campbell, the current that is coming towards the node, what happened to it? The node with the 20 and the 10, what happened to that current?
Sir, it would split between 10 ohms and 20 ohms.
You sure? Look at the circuit.
Sir, I'm looking at what happens to I2 when I1
is
equal to 0, right?
How would it divide? Some come here, so where the rest go?
Sir, then sir, we wouldn't be considering the 5 ohms.
Why? Who tell if we take the 5 out of the PPM circuit?
Sir, that's what I understood must happen. Sir.
Come on. The 10 and the 5 are in series. So it will be divided between 20 and 15.
There's an open circuit we're looking at.
But the open circuit is over here, so. Is the port that is open.
Oh, understood. Yes, sir. Fine. Yes, sir.
All right. So after 15 minutes, H22 is equal to I2 over V2, with I1 being equal to 0. So it's 20 in parallel with 15. However, what we are interested in is I2 over V2. So that gives me 35 over 300 Siemens. So the hybrid parameters would be as shown. Any questions? All right. So let's go back to our circuit. Yes. All right. Now, here are our hybrid equations. All right. Now, if you recall, when we looked at the impedance parameters, we had made some substitutions for the input current. Remember, we had an expression for the input current. We had that I1 was equal to 15 minus V1 over 10. And we also had that V2 was equal to minus 4I2. Okay? So I'm going to make those substitutions into this set of equations because now we have the hybrid parameters. I'm using them to define our circuit or to analyze our circuit. So we're just substituting. This would be I1 and this would be V2. Okay? So making the substitutions. And of course, we have just calculated the values for EH1, 2, 2, 1, and 2, 2, and 1, 1. Making those substitutions, and I'm showing them now in blue. All right?
Sir, when you finish, you can just keep up the second more look at the circuit.
It's the same circuit that you used twice already. Nothing has changed. It's the same circuit we used for the impedance and the admittance parameters. All right? Are we finished with this?
Yes.
All right, so making those substitutions, simplifying, we get these two equations, and if you solve them simultaneously, you'll get the same answers that we had before. Again, reinforcing the point we have been making so far, that in terms of the parameters, doesn't matter which set of parameters we use, we can use them to analyze our circuit when we have a load and a particular input. So if we can change the load, we can change the input conditions for the given circuit, and we are good. So I have used as an example an amplifier circuit. So, you know, we can change what we have in terms of input to the amplifier, in terms of output to the amplifier. Yes? So let's think of it now. The input I may change would be the microphone, the type of microphone that we're using. And that will give me a certain input to the amplifier. The output would be a certain size speaker. Yes? But the amplifier doesn't change. And let us say the circuit that we have is represented by those parameters. So I can say what the volume would be through that speaker based on the input that I have. All right? So just to also bring some link this to what you would have done in electronics. For this circuit, all right? Is this circuit unfamiliar to anybody in the class?
Yes, sir.
Good. It's unfamiliar?
Yes, sir.
Yes, sir.
Sir, you want an honest answer, sir?
All right. Okay. Well, you soon see it. Put it that way. You'll see it soon. So let me just
Wait, sir, question,
bring you
sir.
back now to what we said earlier. We started at H11, yes? And we said that H11 was the input impedance. Okay? Short circuit input impedance. This parameter, that the I in that parameter represents input. Okay? We then also spoke about the H22. And we said that that was the output admittance. The O in this parameter represents output. We also spoke about the reverse voltage gain. This parameter, the R, is for reverse. And then here we spoke about the forward current gain. This parameter, the F, is for forward. The E in each of these parameters tells us which of the legs, so to speak, of the transistor is common to both the input and the output circuit. And in this case, it will be the emitter. So what we have before us is a common emitter configuration. All right? So you therefore have HIE, which is the input impedance, HRE, the reverse voltage gain, HFE, the forward current gain, HOE, the output admittance. All right? So when you do this in electronics, it shouldn't be too strange. Or if you have done it, it hopefully has enhanced your understanding. All right? All right, so moving right along. Oh, come on. Okay, so we have looked at 3 sets of parameters already: impedance, admittance, and hybrid. The final set of parameters that we need to consider are known as the transmission parameters. And the transmission parameters are a little more straightforward than the hybrid. The transmission parameters looks at the input voltage and current with respect to the output voltage and current. So for the transmission parameters, what we have, yes, are V1 and I1 with respect to V2 and I2. And matrix form, we have V1, I1 is equal to ABCD times V2, I2. Now, I don't want you to get too worked up about what you're seeing with this negative. All this is presenting to us is that when I'm transmitting a signal, yes, and I have it at the input, I'm expecting that we are transmitting towards a load. So we would have input, the output would be in the same direction. All right? Because we are transmitting. However, by convention, the two-port network has the output current coming in. So for that reason, you have a minus I2 on the output. That's the only reason why we have the minus I2. Okay? But don't be too bothered by it. You will see that it works out quite easily, quite nicely actually. All right, so this gives us, and I'm just gonna give you all the names. So for your A, B, C, D parameters, for A, the V1 over V2 with I2 equals 0. B, V1 over I2 with V2 is 0. C, I1 over V2 with I2 equals 0. And D, I1 over minus I2 with V2 equals 0. I strongly encourage you not to try and even remember this, but just to work with the equations. So A would be the open circuit voltage ratio. B, the negative short circuit transfer impedance. C, the open circuit transfer admittance. And D, the negative short circuit current ratio.
Sir, can you go back for 1 second, please?
All right, take this first, please.
Okay.
Everybody has this?
Yes.
Not yet, sir.
All right. Let's see, based on what we have done so far, I want you to go ahead and try and find A. Find A for me, please, everybody. I'll come back to you in a couple of minutes. All right. So anybody have an answer for me? Does anyone have an answer?
Over 2, sir.
I get 1.5.
1.5, all right. Not bad. So you went on to B? All right, so for A, all right, A is equal to V1 over V2 with I2 equals 0. So of course that is open circuited. And we want the relationship between V1 and V2. All right, so V1 would be seen across the 5 ohm. Yes, so we are just dividing between 10 and 20. Yes, so we have 20 over 30, and then of course we find the inverse. Beautiful. So you see, it's not too bad. For B or for C, since, by the way, in going to C, the only reason I'm going to C is because we still use I2 equals 0. All right. And then for B and D, we'll use V2 being equal to 0. All right. Okay. So with I2 equals 0, C is I1 over V2. Yes. For this one, it takes a little more thought, but just as simple. Yeah. We want the current through the 20 ohm. And then, of course, if we know the current through the 20 ohm, if I multiply that by 20, then I'd have the voltage across the 20 ohm. So I now have a relationship between V2 and I1. And what I want is I1 over V2, so we rearrange and we get 35 over 100. And that is C. Are we good with this?
Okay, I'm excuse sir. For B, what did you say it was, sir?
We haven't done B as yet.
Oh, all right, sir.
All right. For B, we now have port 2 short circuited. So for A and C, we had it open circuited. For B and D, we have it short circuited. So I put in my short circuit. And then I want to find oops, let me just adjust this. Okay, my adjustment not that great. Okay, so let's see if I can make an adjustment to the. Okay, so let's see now. With port 2 short circuited, that's a lot better. We have B to be equal to V2, V1 over I2, with V2 being equal to 0. All right. With that short circuit in place, what we want is the relationship between this just a minute. We want the relationship between this voltage and this current. So I2 would pass through the 10 ohm resistor. Yep. And so V1 with V1, that voltage would be the voltage across here. It would cause a current to be going in that direction. Yes, which would be the negative of I2. And we know that by convention, I2 is flowing into the network. Fair enough? So rearranging, we get V1 over minus I2 to be equal to 10, which is equal to B. Any questions?
So you can go back to the till you find A. I left out.
Hey, but you were the one who gave me the answer, ain't no good man.
No, sir. No. I want to see the way you work different from me.
Same like you, man. All right. And then we go to D, because for D, we'll also have port 2 short-circuited. And D is I1 over I2 minus I2 V2 0. And so they're supposed to be minus. Just put in the minus there for the I2, yeah? So we need a minus right here. And so if you look back at the circuit, if we just apply current division, if we apply current divider, then the current that will flow, I1, would divide between 5 and 10. No, it is between 5 and 10, Ms. Campbell, because we have the short circuit over here. So it means that the 20 ohm would be bypassed. All right? So it's being divided between 5 and 10.
Yes, sir.
And so the current through the 10 ohm using current divider is 5 I1 over 15, which would be the negative of I2. And we want I1 over minus I2, so we get 3. All right. So, students, we have looked at a simple 3 resistor network, and we have found the admittance parameters. We have looked at the impedance parameters. We have looked at the hybrid parameters, and we just looked at the transmission parameters. So I want to put all of them together. So we can look at all the parameters that we have found for this one little network. So for the network, the parameters are as shown. All right, so we have y 0.3 minus 0.1 minus 0.1, 0.15, well, you can read them, right? So these are the parameters we found for the network. Yes. And what I want to know, look at, is that when we have these parameters, you would have noticed that for some parameters, it was easier to find than others. So for some students, it may have been easiest to find the impedance parameters. For some, you may have found the T parameters easier to find. And again, for others, you'd you'll be much, you find the admittance, the hybrid much easier, or the Y. You know, people have different skill sets. Fair enough? However, depending on what you may find most simple and what you're doing with the networks, some parameters become more useful than others. What do I mean by that? When I'm connecting, when I'm looking at the output of a network going directly into another network, we refer to this connection as being cascade, not series, but cascade. So this is the input of network 1. All right, so that's network 1, this is network 2. This is the output of network 1, this is the input of network 2, and this is the output. Okay? If we have this setup, what we will find is that it is best if we had the transmission parameters of both networks. If I had the networks connected in series, for example, it may be best that I have the impedance. Then again, if they are in parallel, it may be best if I have the admittance. Good? So we will need to move from one set of parameters to the next. I did give you a simple exercise. I did ask you to go through the exercise of finding the inverse of y and to prove that it's equal to z. I hope you actually did that. Assuming that you did, you would have found, you know, I mean, you can invert a matrix. I don't need to go through all of that. However, what we're going to look at next, and then I'm going to go into a couple of questions. We are now at 2:20, and hopefully we can get through. Good. So I'm going to look at a little exercise, and then, or you know, introduce you to something, and then we take on a couple of questions and run through them. All right. So this big matrix or mother matrix that we have is what we're going to use in moving from one set of parameters to an next set of parameters. If you note, the matrix consists of 16 submatrices, yes? And along the leading diagonal, you have the parameters that we just looked at. So here is how we use this matrix to move from one set to the next. You're going to consider what you have. Listen carefully. So for what you have, you're going to move vertically. You get that? So what I have, I move vertically. So as an example, if I have the admittance parameters, I'm going to move vertically. Because here's the admittance. I'm going to move vertically, yeah? And if I want the transmission parameters, so what I have are the admittance, what I want are the transmission. I'm going to move horizontally with what I want. So I've moved horizontally. Where the two intersect will be the matrix that I use to convert. Need me to do that again?
Yes, sir.
Yes, sir.
Definitely.
All right. So, let's see now. Ms. Brown.
Yes, sir.
All right, tell me which parameters you want to convert from. Just tell me the setup.
Transmission.
All right, so you want to move from transmission. So here's the transmission. Here are the transmission parameters. I'm going to move vertically. Okay, Imani, tell me which parameters you want.
Hybrid.
Hybrid. Here are the hybrid parameters. So I move horizontally. They intersect at this point. So this matrix will be used to move from transmission to hybrid. Easy, right?
Okay, so let's see what I say.
Huh?
Sir.
Yes, sir, let's see what I say.
What you have to move what you have to move vertically, what you want to move horizontally, wherever they meet.
As simple as that.
Okay.
It's like a matrix again, sir.
Well, all right. Okay, so just to know, sort of tie up everything that we have spoken about since for the last 3 weeks, really, well, 2.5, yes, on 2-port networks. Let's do this simple question. Take this question for me. All right. Any suggestions? Anybody? Mr. McKenna?
Yes, sir.
How are we going to start this one?
All right, judging from what they gave us here, we can see that I'm taking that as the admittance parameter.
Okay, why?
Because when we look at the relationship in the equation, we have relationship being between the input current and the voltages. So,
okay.
So that will give you the admittance. So when we make port 2, 0 by short circuit port 2, we have Y11 as 0.003. And if you were to make port 1, 0, we would have Y12 as negative 0.015.
Beautiful. All right.
Yeah.
So where do we go from there?
I'm thinking. Thinking.
What other important bit of information do you have? Mr. Cahoon, what other important piece of information do you have?
Not sure what to tell you right now. I'm not seeing all of the questions, sir. I don't know if you can make the display much smaller. I'm not seeing all of question B.
Forget about the question part, man. Look at the information you're given. What are you given? So what important information are you given?
It is a symmetrical network.
Huh?
Symmetrical.
It's symmetrical. All right, thank you very much. So the fact that it is symmetrical, what can we derive from that?
Characteristic impedance.
All right. In addition to that, what else can we say?
Since it's symmetrical, then the transfer would be the same because when you're looking from both sides, it would be equal. So then
what transfer value?
Negative 0.015.
Right, so it means that we can find the other equation. So I2 would be equal to?
I2 equal negative 0.015 V1.
What does 0.03 represent?
Total.
Oh, 0.003. What does it represent?
The admittance Y11.
Yeah, but what the name?
Short circuit input admittance.
So it's the input admittance. So if it is symmetrical,
Yeah, it equal from both sides.
exactly. So the input and the output must be the same.
Right.
All right. So what will be the second equation?
I2 equal negative 0.15 V1 plus 0.003 V2.
Thank you. So remember what I said when I was about to give you the question. I said I was going to test you based on everything we have done so far. So I've just tested you on your understanding of symmetrical or symmetry in your network. I've tested you on your ability to identify the parameters. And having identified it, you then would be able to write the second equation. So just in summary, yes, the key points, because it is symmetrical, it means that the input and output characteristics are similar. And that is also true for the transfer characteristics, which Mr. McKinnon stated. The equation represents the input current in terms of input and output voltages. It means that we are dealing with admittances. Okay? So, based on that, that's our corresponding equation 2. Anybody unsure about what we have just done?
To an extent, sir.
Huh?
To an extent.
All right, tell me why you're not clear on.
I get that because 0.003 would be the input. Would be the input that we would have got.
Yeah, man, I'm listening to you. Go ahead.
I think it's part of where the negative 0.015.
But remember, Mr. Facey, remember this 0.015. Okay. I think I see where your confusion is. Is it that the negative? Because you see the negative, you are thinking A, B, C, D?
Oh no, sir. I got that it's in the admittance.
Okay.
I
Okay.
understand that.
So how is it that the negative is impacting your understanding?
I think it's getting the second equation would be my problem.
All right. Remember that universally the equation says Y11 V1 plus Y12 V2.
Yes, sir.
Agreed? You agree with that?
Yes, sir, I agree.
But if I end up having minus 0.015, what does that really mean?
That
If the equation says y equal a plus b,
yes, sir.
but then I get 5 is equal to 3a. No, that's a bad example. So the equation is I is equal to y1 v1 plus y12 v2. Good, that's the equation. But then I end up, when I now putting the numbers, I have I1 is equal to 4v1 minus 2v2. What does that read? What does the minus tell us?
The direction.
No, it's telling me that I'm adding a negative value. So it means that the y12 is negative.
Yes, sir. Just a negative number.
So I'm adding a negative. So y12 is negative, which means that y21 must be negative.
I see that, sir.
All right?
Yes, sir.
That's all right. I'm not going to stress it today. It's the first serious question anyway. So you don't have a problem in terms of the symmetry?
No, sir.
All right, cool. So I don't need to go back through this then. All right, so the parameters, taking them from what we have here, would be 0.03 minus 0.015 minus 0.015 and 0.003.
So I'm not sure if you're expanding your screen or something that's about it. A part of it is cut off.
You're using a computer?
Yeah.
Just press Alt.
Problem solved, Mr. Atkinson? Even if you're not seeing it, here are the parameters. Just put them in a matrix. All right? So now that I have the Y matrix, so I have that. What did the question ask you for? It asks you for the hybrid parameters.
Hybrid.
So you are now going to go to your conversion matrix. I have Y. I want hybrid. That's the conversion matrix. So this is the matrix that we're going to be using to convert. Where delta, all right, we talk about delta. Delta Y, that's just the determinant, eh?
Yes, sir.
And so delta would be the product of the elements on the leading diagonal minus the product of the others. And that gives us 0.0000216. All right. All right. So substituting in the matrix, this is what we have. So this would be the matrix, the parameters, the hybrid parameters. Any questions, students?
Sir, is there a reason why 2 became why the negative 0.072 is there even though you didn't have any negative signs?
Again?
When you divide 0.00216 by y11, you have a negative.
Excuse me, sir.
Sir, he's saying your
Yeah, I'm looking back at it. So it's delta y over y11, right?
Yes, sir.
All right, so that should be 0.072.
Yes. All right.
Thank you, Mr. Thompson.
Welcome, sir.
Sir, isn't the 5 to the negative?
Pardon me?
I think that's what
No, it would have been positive.
Minus y1 over
Times
y.
negative.
It's the rest of it is fine. All right, so the second part of the question asked for, what did it say? Listen up. The second part of the question says, hence determine the efficiency of a source of EMF 10 volts and internal resistance 1.5 ohms in supplying power to a 5 ohm load via the network. All right? We're not going to get bogged down with the efficiency. What we are interested in is how do I use that information or how do I input that information? So here's my network. What I have for the network are the parameters. And the information that we're, why do I have a 4 ohm? Anyway, the question said 5, but I have 4 here. I don't know what's wrong here. That's just me. I'm sure I did it. Didn't do it while I was hungry. So let us see. Okay. So this should be 5. But I think I did all the calculations with 4. So let's change the question to 4 ohms, all right? Instead of 5. So here's my source, EMF 10 volts, internal impedance 1.5 ohm. Okay, so from this, what would V1 be equal to? With given all that, given the information that we have here. So on the input side, what is V1 equal to?
Ten minus 1.5 I.
Yeah.
I1.
I1. All right, so V1 would be equal to 10 minus 1.5 I1. And V2? What's V2?
I2 times 4.
Again?
I2 times 4. Oh.
I've done this enough times for you not to make that error again.
Minus 4 I2.
Thank you. So V2 is equal to minus 4I2. And V1 is equal to 10 minus 1.5 I1. Let me double check this because I actually had it correct, So the error would have been further up. The error would have been here because this 0.003 is obviously smaller than 0.015. Now, so go.
Yes, sir.
Yes, sir. It's fine.
This is negative. So the delta is negative. You with me? You see what I'm correcting?
Yes, sir.
So instead of this being 0.00216, it is minus 0.00216. So it means that what we had here with the minus is correct. Because that would be minus. Are you with me?
Yes, sir.
Okay. All right, so back to this. So we have the input voltage and current. We have the relationship between them. We have the relationship between the output voltage and current. Now you have a choice. You have a choice as to whether or not you want to use the admittance parameters. Well, let me double check the question just to make sure. Oh, sorry, you don't really. It tells you hence. So you have to use the hybrid parameters, all right? So using the hybrid parameters, we have V1, and that's V1. And then we have V2, and that's V2. Okay? And so we are left with the two unknowns, which are I1 and I2. So if we simplify this, or these, and solve, we get I1 to be 21.04 milliamps and I2 to be 147.755 milliamps. And then you can use that to find the power dissipated. All right, so it is now 7 minutes. Any questions here, gentlemen, on the list? Come, folks. Speak to me. I know it is not that clear.
Sometimes when you're not hearing a question, that's where the problem is, you know, sir. Because I'm saying sometimes when you're not hearing a question is a big problem, because it means you don't even know which question to ask. So we have to just take some time and absorb it a little bit first.
So we passed that already, you know. I thought from when we were face to face, we all agreed that there's no such thing as a foolish question. I thought we agreed on that already.
No, you know, say not a foolish. I just saying that more time in order to formulate a question, you have to have a level of understanding before you can.
All right, fair enough. I won't argue with you on that one. So what I'm going to do, let's see now. I'm trying to be, because it's important. I've made it abundantly clear already to the powers that be. I'm not sure why they are insisting on it, that it is pointless. It's really pointless for students to have a tutorial immediately after a 2-hour lecture with networks.
Yes,
right?
sir. Yes,
It's
sir.
a pointless exercise.
Yes, sir.
So what I'm going to do, I'm going for the 5 minutes, I'm going to ask you to just write down these 2 questions, and then I will go through them in detail with the group tomorrow. If those who have class this afternoon want to turn up tomorrow, fine with me. It doesn't matter. Otherwise, those who would have had the class after this, you will access the tutorial video for tomorrow.
Sure.
Right?
What time tomorrow for class?
It's 6 o'clock, I think.
Okay.
All right. So you all do your screenshot thing and screenshot that. So that's question number 1.
Sir.
Yes.
I haven't been accepted to Schoology as yet.
Oh, yes, man. All right, so that's question number 1. Question number 2.
Sir, when it says from first principles, is that the process to develop the matrix?
Hmm?
When it says from first principles, is that the process?
And you gotta find the relationship between V1 and I1, V2 and I2, V1 and I2, etc.
Yes, okay.
So what we did for the little pi network, you're not gonna do it for all that we have here. Understood?
Yes, sir.
All right. And then question number 3. All right, so this is question number 3. And once you have taken question 3, then you can leave the room. All right.
Good evening, sir.
Come on. Afternoon.